Thank you, Franz. Thank you, Carl, for inviting me. I'm really honored to be here. I love giving talks. I love talking to students, and it's really a pleasure to be here. It's my third time in Philly. I've had my share of cheesesteaks, as I mentioned, but it's my first time at UPenn, and so it's really exciting to be here. And I think that what I'll be talking about is just a subset of what Farhad mentioned. I think it fits very well into what I'm kind of learning about the way this interplay of robotics and learning and kind of mathematical control works at UPenn. So I hope that this kind of hits the spot for many of you. So I will be talking about system resilience and guaranteed performance in the face of unexpected adversity. Now, this is the big bag of words, right? There's 10 words here. And so just to kind of provide a motivating example for what I mean by this and what I'll be talking about here, let me just play a 3-minute video, a 2-minute video. It has sound, so I believe you should hear it. There's also subtitles at the bottom.
6-8 Zulu is declare an emergency. 6-8 Zulu, declare an emergency. 6-8 Zulu, declare an emergency.
6-8 Zulu, Roger. You want to come in for runway 20?
I don't know if we can get there. 6-8 Zulu.
6-8 Zulu, say again?
I don't know if we can get there. We just lost our engine power. Something's happened.
8 Zulu, Roger. Wind is 230 at 10. You're clear to land any runway at Santa Fe, altimeter 3020. Can you give me some information?
Okay, I'm 6 about south. I've got a big vibration going on. My prop's going bad here, and I don't know what's going on. And I've been at 8,500. I don't think I can clear. I don't think I can get to the runway.
Make straight in for runway 2 if you can, but the wind is going to be a tailwind, 230 at 10. You can have any runway you want, clear to land.
I don't know what's happened here. I have no oil pressure. I have no oil pressure.
Right on the final for runway 2. You're 7 miles from the airport.
I don't think I can get. I'm not going to make it. So, let's see. Where's our best place to go? I'm going to try to stay away from that ravine. Freeway?
I-25 is in your vicinity, and maybe the frontage road off of I-25. There's 3025.
3025. I'm just not going to make that. I'm not going to make it.
We're 6-8 Zulu, and can you tell me what's going on now?
Try to land on the freeway here if I can. My engine. I have lost the engine, and I'll do the best I can here. Don't know if I should try to land on the freeway here or on the frontage road. I think I'll take the frontage road.
That'll be a good idea if you can. The Santa Fe winds are 240 at 9er. I've landed. I've landed.
So these last few seconds I just put in just so that you know that the file everyone's good. And I promise you, throughout I'll have a few more videos in this talk. I want to promise you right now, no one died in making of any of those videos. So you'll see it'll get weird. You'll need this caution. So let's kind of discuss what happened here. So a pilot was planning to land at Santa Fe. And over time, there seemed to be failures. So there was one failure, and somehow it also seems that these failures are increasing. There's changes that are happening, and in the end, or somewhere near the middle, he decides that he can't land at Santa Fe. He doesn't believe that he can get there, and so he starts looking for kind of the next best option. And he's like, okay, I'm going to try to stay away from this ravine. And then he chooses the interstate or the road next to the interstate, and then he manages to land there. So ultimately, what we're talking about here is he's trying to develop some sort of a maximal understanding of his capabilities in the face of limited knowledge. So some things broke. By the way, this was a tiny airplane, but it was not a 737. But so some things broke. Some control surfaces are no longer operating, or in this case, it was the engine. And he is trying to land safe. Now, this is not a new problem. If you look at kind of the classical methods of adaptive control, of robust control, they try to say, okay, we are trying to figure out a control law that will reach the objective under some lack of knowledge of the system dynamics. But here's the thing. In this case, this was impossible. It was impossible, or at least the pilot believed that it was impossible to reach this objective. So this was not a question of, hey, can I figure out a control law that will allow me to now land at Santa Fe? Because there's a good chance that there is no control law that will allow me to land at Santa Fe. I simply don't have the actuation capabilities to do so. So what happened here is, so the pilot intended to land at Santa Fe. Now this is no longer certain. So the pilot tried to figure out, okay, where do I think that I definitely can land, possibly with the understanding that things might even be progressing towards getting worse over time. What are kind of the guaranteed spots where I think I can definitely land? And so this is what the pilot did. He decided on what he figured was a reachable target. That was the frontage road, and then he planned how to get to that reachable target. This is the framework that I'm interested in developing. So not just the framework of adaptation, but the framework of figuring out, faced with a partial lack of knowledge about dynamics, environment, whatever is going on, figuring out, hey, what are the things that I can guarantee I can complete? What are the missions that I definitely can pursue? And so this is mathematically, I think that this abstract framework is applicable across domains. So it could be in something like a network system, like a power grid, where some of your components fail and you want to see whether you can still ensure the performance of the overall system. Whether it's in a kind of a UAM, so urban air mobility framework, where you might have some bad actors who are not following the particular rules or that suffer damage. We're right now working in a robotic example with a NASA grant with a tool or their hardware called Owlet, where we are playing with, hey, some parts of your robot fail. What are the capabilities that we can still complete? What are the missions that we can still complete given this failure and given our possible lack of knowledge about the failure? So my entire talk is basically predicated on the claim that bad things, disasters, malfunctions, physical damage, hostile action will unavoidably occur for cyber-physical systems. No matter how much we try to protect these systems, eventually things will definitely go wrong. And once they go wrong, we might be interested in a few things. The first question that I have is what I call a posteriori resilience. So when a disaster strikes, can I figure out a way to certifiably drive the system to complete its mission? This is not necessarily a new question. It's an interesting question. It's a classical question that is at least partially very well answered by adaptive control, by robust control. There's a bit of a question on kind of certifiability of things. It depends on different methods, but this is something that's pretty standard. I claim we should do more. I claim we should discuss a priori resilience. Can I design the system in such a way that after a wide class of adverse events, after a wide class of disasters, I know that I will be able to certifiably complete a wide class of missions? Now, the way that I phrase this question is it's generally unlikely, right? If something happens to you that is so terrible that you can't really do anything, then yeah, you won't be able to complete any mission, right? So generally, we can somehow feel that this is unlikely, but we're still willing to play with it. And then the third thing, which the second thing then leads us to, is guaranteed performance. Okay, so when a disaster strikes, can I, given my current partial, imperfect knowledge about what happened, can I determine what missions, what tasks the system is provably able to complete? So these are kind of the three things, or these two things are what is going to kind of drive the rest of my talk. And just to provide a mathematical framework of what I'm talking about, and of course these all things can be thought of in variety of frameworks, discrete time, stochastic, whatever it is. I'm going to keep to kind of standard continuous time ODEs. So I'm going to be considering a system that's x dot equals f of xu, where u is some sort of a control input that lies in some set u, and x is the system state. Now, I will be considering and possibly combining three, let's say, classes of adverse events. One is change in dynamics. So because of physical damage, my f is no longer f. It is something else. Class number two is partial loss of control. So I used to have 6 actuators. Someone took over one of my actuators and might be plugging in bad inputs. This is a framework that you could think of in terms of network control. If someone took over a part of your entire system, so some of your components. The third part I will be mentioning is actuator degradation. So the dynamics are still the same. I still have control over my actuation capabilities. I just can't plug in some of the things that I used to be able to plug in before. So when we combine those three things, really this equation x dot equals f of xu, u and u, kind of changes to x dot equals f hat. So f hat is the new dynamics, possibly partially unknown. X of uv, where u is now the part of the actuation capabilities that I still have control over, and v is the part that is possibly adversarial or random, or call it whatever you want. And u and v together now live in this degraded set of possible inputs, which is u hat. So I will be continuing with these kind of models throughout the talk, and I'll kind of start going from right to left, from seemingly less difficult cases to more difficult cases as I discuss these possible disasters. So let's start with actuator degradation, and just kind of provide a motivation that's not to do with airplanes or things like that. So I found this on a sailing forum where a person basically described exactly the situation I care about. So the rudder on his sailboat, it's supposed to be able to go left and right, but it's somehow bent and jammed. And so it can't go to the right anymore, or at least it can't go as much as it was able to go. So he can still control the rudder, he just can't control it to the extent that he was able to before. And you could imagine such things in cyberspace, where you could have a denial of service attack, where because your bandwidth is taken over by, or part of your bandwidth is taken over by an adversarial actor, you have less capabilities to respond in some way. So in such a case, we have x dot equals f of xu. So the dynamics didn't change, everything is still the same. It's just that u is now in this u hat. And I'm interested to answer the question of, okay, what are the things that what are the missions that I can complete? And kind of the easiest thing of those is, okay, what are the states that I can reach, for instance? So in theory, this is a simple question. If the dynamic, given that my dynamics are fully known, if I have some bound on the degraded actuator limits, or I know the exact degraded kind of actuator limits, then the reachable set can be under approximated by computing the reachable set for this system with the under approximated actuator limits. And now we are happy. Of course, we are entirely unhappy. In practice, reachable sets of even fully known nonlinear systems are not computable in real time. Even not in real time is difficult. And in particular, we care about things that are provably in this reachable set. So what I can definitely guarantee, so meaningful under approximations. That's difficult. What people do often is in advance, they compute what they call an operational envelope for the nominal system. So this is some sort of a stand-in for the reachable set obtained through exhaustive testing or through whatever it is. And this is computed through years of design and simulation and testing. So this is not something that we can do in online and on the fly. However, we are in a good situation here because our new system is essentially the same as the old system. It's just that the actuator limits have been degraded. So we can assume that we know this reachable set for the old system, or operational envelope, or whatever you want to call it, for the nominal system, and we know a bound on the degradation. So our computation of the degraded reachable set shouldn't start from scratch. We know that there's some sort of a relationship between the old reachable set and the new reachable set. And so to kind of formally, sorry, is that a question?
Yeah,
Yeah.
you're assuming that you have as a subset of you then.
Yes, I don't necessarily even need to. So in the recent papers that we have, we generally assume just a Hausdorff distance of, so a bound on the Hausdorff distance of U and U hat. But the motivation is that, yes, U hat is smaller. But yes, good question. And so a lot of these things that we are developing don't really need it. Okay, so what the kind of foundation of how we're trying to build this under approximated reachable set is this idea. If I have a newly available control signal, so the control, or sorry, still available control signal, so available after the degradation, if that control signal differs from a desired nominal signal by no more than epsilon, then the state that's reached by this new, by using this new control law can't be too far from the state reached by the old control law, because the new control law and the old control law are no more than epsilon distance in some meaningful norm. Now, this is very vague, right? I said, oh, it can't be too far. Well, okay, it can't be further than some h of epsilon. How do I determine h of epsilon? What is that? And so I'll just kind of give a brief story. This kind of looks like Grunwald's lemma, right? The difference in the dynamics that are generated by the two control laws, if we can somehow bound them, then Grunwald's lemma should give us over time some sort of a difference or some sort of a error distance between the two trajectories. Turns out we can do slightly better using something called the Bihari inequality. So if we have, if we know that the difference, or if we know that the system dynamics satisfy some generalized version of the Lipschitz property, then we can speak about the difference between, then we can bound the difference between the two trajectories using some sort of an integral inequality. My point is, I'm not going to go deeply into this. This is a more general version of the Grunwald's lemma. So intuitively, this result should depend on the wildness of the system dynamics. So if the dynamics are very tame, then a small change in the control input should not cause a large change in the trajectories. On the other hand, if the dynamics are very wild, then the difference could grow very quickly. And the kind of proof is similar to the Grunwald lemma proof, where we kind of try to bound this difference between the new dynamics and the old dynamics using some sort of a Lipschitz property. It's just that we can do a bit better than Lipschitz. Point is, we can do Lipschitz if needed. We can do better if more information is available. So the idea now, using this theory, is that hey, if the Hausdorff distance of the nominal set of control inputs and the degraded set is bounded by n, that means, by definition, that for every nominal control signal, I can find an allowed degraded signal within an M ball. Each state in the nominal reachable set then has an analog or has a twin, if you want to call it, in the degraded reachable set that is within the ball of size h of m. And we can do somewhat better. It doesn't have to be a ball. We can do it separately on all the coordinates. It can be a rectangle, but this is the idea. So if my old reachable set is the gray, that means that for every gray point, there exists a red point. So red is the new reachable set. There exists a red point that's within some sort of a rectangle that's centered at the gray point. So for every gray point, I can get a red point. Now, there's still a little bit missing. So I'm still lying a little bit here. We kind of have an idea of what these red points are, but currently it's just kind of a point cloud, right? We don't have the idea that everything in between, or we don't have the proof that everything in between is also still reachable. Technically, a lot of these gray points could just point to the same red point, could just map to the same red point. So we can fix that by also showing that any state in the boundary of the degraded reachable set maps to a nearby state on the boundary of the nominal reachable set. So for every state in the boundary of the red, there is a state in the boundary of the gray that's close to it. And this is how we fill the blanks. Yeah.
You're currently not making any assumptions on how this mapping is happening. Right? So you're not saying you're mapping to the closest possible point.
No, I'm just saying there exists a point. For every gray, there exists a red. This is a very interesting question, by the way, that you bring up, and something that we're currently working on is, okay, what do I actually do with this? How do I determine that point? And how do I figure out the control law that's actually going to drive me to that point? And that's a far harder thing. But right now, I'm just saying, okay, I know what I can do. I don't know how to do it yet. Okay, so to kind of show you that this does work, at least on some sort of a reasonable example, I'll provide an example of so the Norbin's ship model. Yes, my student was inspired by that picture of the rudder. Anyway, the original reachable set of the system is this thing in blue. Now, the degraded reachable set is red, or whatever this is. We provide an under approximation for this degraded reachable set. We don't hit everything, so what we get, which is in green, is smaller than the degraded reachable set. But at least it's a decent under approximation. It's not like we under approximated a big thing with just one point. Of course, these under approximations get worse over time. And so in a sense, unless we have very good bounds or something significantly better than Lipschitz, as time progresses, asymptotically, the approximations will get worse and worse. And so we can kind of do this for kind of short maneuvers. And this is what I will actually do. So I'll consider a boat that is, I don't know if I can stop this, can I? So we will consider a boat that is traveling from here and it's trying to get somewhere here. The boat, there's an unsafe set around some rock or buoy or whatever it is. The unsafe set is marked by this circle. And so the boat originally plans a course that takes it to its destination while not touching the unsafe set. It, sadly for the boat, it originally comes pretty close to the unsafe set, right? That's what we need for dramatic tension. And even more sadly for the boat, it will suffer a damage that will partially degrade its capabilities right about now. So at this point, the boat has degraded capabilities. And what we care about is figuring out whether there exists a path, whether there exists a part of the reachable set that is outside of the blue circle. If everything in this under approximated reachable set is inside the blue circle, then we have no guarantee that we will not smash into the rocks, and maybe the best thing to do is just jump out or call for help or whatever it is. In this case, and this will kind of show itself now more, we can show that there does exist some part of the reachable set that is outside of the buoy, or that's outside of this prohibited set, and so the boat continues. Now, I want to be very clear here because sometimes I sell this slide by not mentioning what I'm going to mention now, but you seem like a very kind of concerned audience here. So how did I come up with this control law? Yeah, that's a lie, right? Or it's not a lie, but right now this is done by hand. We just know that the control law exists. my theory guarantees that the control law exists. And then we can start playing with trying to design this control law. And this is what my student did, and we designed the control law. Of course, down the line, you care about this second part as well. How do I figure out how to actually escape from this buoy, or not just whether there is a way? Yes.
In this case, isn't it possible to compute the possible trajectories up to a planning horizon and then choose one that's safe?
Well, yes, but no. So yes, in the sense that if we were working with discrete time, then you could do that in the sense of you can just use a kind of a decision tree of, okay, every possible option and then every possible option, and this gives us all the possible trajectories. I'm not working with discrete time. Also, over a longer planning horizon, this will computationally kill you even in a discrete sense. And so your question ultimately is a good question. It is equivalent to essentially finding a reachable set, which for nonlinear systems, continuous time is difficult. So yes, it's a natural way to go, and that's what we're kind of trying to do. Okay, so let's say I sold you on this actuator degradation thing. Let's go into the second part, where it is not just that the actuator is degraded, it is that I no longer control the actual actuator. I have a video here. Let me just play it.
Left to right, the Stealth F-117, ladies and gentlemen.
Again, promising no one died. You look very concerned about this. The pilot jumped out. The airplane obviously did not live past this. So what I care about here, what I want to mention here is you can see in this kind of the last part of the video when it's in slow motion, you can kind of see, maybe let me do it once again if I.
Left to right, the Stealth F-117, ladies and gentlemen.
There's an oscillation that at first is kind of natural, and it is a perfectly allowed oscillation because that's a part of the airplane's control surface. That's an element. But this, because of mechanical failure, this oscillation is not actually caused by the pilot. My understanding is that there was some sort of a screw issue, and that basically the elevon started operating on its own, kind of random. The pilot clearly did not or was not able to cancel out this undesirable actuation. And that over time kind of led to disaster. And this time, in this case, it was a really short time. So this is exactly what I call the loss of control authority, or loss of control authority. I have now my actuators, and I will split them into two pieces, U and V. U is what I still continue to have actuation over, so the pilot still had access to all the other control surfaces. V is an uncontrolled system input. And I want to be very clear that this is not a small disturbance. This is not something that's often considered in kind of robust control. Hey, there's some sort of a bound or some sort of a wind where we know the maximum wind speed. This is an input whose size, whose magnitude is the same as would have been allowed to the pilot originally. So it goes to full actuation. Ultimately, this is a two-player game. I have one player, which is the pilot, the controller, who is trying to reach a state, complete a mission of some sort. I have the second player, who in this case was the environment, but who could in the worst case be some sort of an adversary who actually puts in bad inputs, who wishes to obstruct player one from reaching its, from completing its mission. These players play simultaneously with possibly odd coupling between them. One player can kind of make actions that disable the other player from doing anything. Their control inputs affect each other. So it's some sort of a difficult two-player game, right? The question that we are wondering is, can player one win? So regardless of what player two does, regardless of how the environment operates, can player one win? And we can ask these questions in kind of more sophisticated ways. Yeah.
How do you like even distinguish between you and me in the first place?
So far, and this is a very good question, I am assuming that I know what broke down, and I'm able to read the inputs that I'm not able to act. So I know what player two is doing, and I know who player two is. I don't know what they'll do in the future, but that's a good question. Yeah.
But you and me, do they happen at the same time? Because in games, you would assume they happen, sequentially.
So they happen at the same time in this case. And this is a bit of an issue that I will mention later, which kind of, hey, how can I actually know what was produced, what my opponent produced exactly at this time? There should really be some sort of a delay, and so we're playing with that now. But at least for the sake of exposition, I'm saying yes, they play at exactly the same time, and each one, or at least you can see what B did, I guess, while making its choices. So I guess B is slightly before you, or whatever, however you want to call it. So the questions are, can P1 win for any state where it wants to go? Can P1 win if there's a time limit? All of these things. The intuition is this. So the intuition is kind of given by what I was saying when we were looking at that video. I said the pilot was incapable or didn't cancel out this bad actuation. So intuitively, player one wins if player one can cancel out, in some sense, the adversarial inputs and still retain some useful control capability in order to fight or exploit the kind of drift. So still do something meaningful after canceling out this bad input. Now, for linear systems, and I'm kind of mentioning this for the sake of mathematical curiosity, fighting the drift, if you have a bounded input set, is impossible, because if the drift pushes the state towards infinity or towards zero, if you far enough from zero, the drift will be stronger than you no matter what. So this gives rise to some sort of conditions on basically the eigenvalues need to be zero. But of course, we are often not interested in unbounded states. We are interested in some sort of bounded state spaces, bounded sets of states to reach. And in that case, fighting the drift may potentially be possible. In all cases, the intuition still holds that the available input needs to be in some sense stronger than the adversary. That's the idea. So in a formal setting, I'll introduce this for linear systems. If my original system equation is x dot equals ax plus b bar u bar, how I will model this loss of authority is b bar splits into two submatrices, B and C. B is the submatrix that denotes the effects of my continued control inputs. C is the effects of the bad control inputs, of the adversary's control inputs. Then the notion of available input is stronger than the adversary is, and we kind of showed that it's almost the same as saying zero is in the interior of this set. What I mean by that is, for everything that the adversary does, there exists a U which will cancel out whatever the adversary does, and not that, but I'm slightly stronger, and that's why I need this notion of interior. So I can cancel things out, and I can also have some small actuation that I still am able to perform. Okay, so we kind of have some ideas on evaluating some necessary, sufficient, whatever you want, conditions, on evaluating this resilience to the loss of authority. Now the question I want to pose is, how resilient is a system? And so the kind of motivation for that is this. If I can reach a target before a bad thing happens, and I can reach the target after the bad thing happened, by definition, the system is resilient. However, in practice, if I used to be able to go somewhere within 2 minutes, and now I'm still able to get there, but it takes me 6 hours, right? My resilience is not very useful. So I want some sort of a quantitative measure of, okay, how much can the adversary hurt me? And so the way we formally frame that is we create the resilience quotient. And so it is a fraction, or it's a quotient of the nominal time optimal reach time. So how long it would take me to complete the mission if I was proceeding in an optimal way and the bad thing did not happen. There was no disaster. And the worst case time optimal reach time with adversarial input, which you can argue, and I kind of mentioned that whether it should be soup in for in soup or whatever it is. But so in this way, I framed it so that the adversary chooses an input such that whatever the controller chooses, the reach time will be large. So this thing is a number between 0 and 1. And it's very nice because 0 means there is no resilience. And essentially we will get 0 if this thing here is infinite. So we are not able to reach the desired state anymore. 1 will mean we have perfect resilience. The adversary did not hurt us at all. Sure, we lost one of the actuators, but that did not change our reach time at all. So every time we will get a number between 0 and 1. Now, what do? How do we compute this number, right? This is seemingly difficult. And now by saying seemingly, I feel like maybe you think I'll be like, no, you see, this is really, no, it's a really difficult problem to compute these, because these are 3 partially nested optimal controls, so infinite dimensional optimization problems, right? This is how. It can be done for simple systems. For driftless systems and integrators, optimal control kind of ends up being an optimization question, because optimal control inputs can be geometrically determined, and there's this notion of direction in which the adversary is the strongest. It's easy to see what's the kind of worst case, and so it's possible to determine this resilience quotient exactly. It's possible to determine the least resilient goal state, and this is a paper that we recently had where we came out with this minimax maximax quotient theorem, which is basically trying to optimize this. Now, okay, you'll be like, yeah.
So the resilience level now we discussed about n, how much n?
Yeah.
So can we have another resilience, for example, how long the power rate installation in the space or?
I just want to make sure I understood correctly. You're saying, can we have a resilience quotient of how far can we still complete our mission? Yeah. So we could. Our current notion of resilience is kind of not geared to that, because it's kind of saying I'm resilient if I can reach everywhere. But I could say, okay, I will call myself M resilient if I can reach every state between, like in an M ball around or something. I could do that.
How is that? So, but your resilience is defined for the specific goal state, you know?
So
use continuous set this
yeah. So you're right. So in this case, the resilience quotient is defined by a goal. I will say that the system is resilient if this quotient is bigger than 0 for every goal and every X. Yeah. So there is still, and this is why it's called kind of minimax maximax quotient theorem. There's still another optimization here where I run through all x zeros and x goals. But so, okay, I figured this out, or okay, I'm lying. My student figured this out for this. What happens for driftless systems and integrators? But okay, but they're real trivial systems, right? At least show us some linear systems. Well, for linear systems, it's already really hard. Even for general linear systems, optimal control signal is known to be bang bang. This is this kind of classical results, but it is impossible to analytically determine. And the set of velocities which the system can take depends on the state. And so the idea there is, hey, let's try to get some bounds on this quantitative resilience. And the big idea is let's use Lyapunov functions for those bounds. So we get a lower bound on the nominal optimal reach time by getting a lower bound on the flow of the Lyapunov function for a linear system. We get an upper bound by getting an upper bound on this flow for a good candidate for optimality. So we plug in something that we think should work well. In practice, I think what we plug in is whatever control input points most towards the goal, and we get some bounds. We do the same thing for the adversarial inputs, so we get bounds on these optimal reach times and adversarial, so reach times given the adversarial inputs. So we can get some bounds, and using these things, we can actually go back to the original problem. Where we can take a model of this is an academic fighter jet. It's called Meyer, and it has, or we consider 4 control surfaces. And we can ask, hey, is the system resilient to a loss of any one of these surfaces? And so what we want to see ultimately is, could the pilot have done something to that 117 where if they played their cards exactly right, they could have survived? And in this case, so in this particular framework, the resilience ends up being somehow connected to the eigenvalues of a particular matrix. And it turns out that the system is resilient to one of these control surfaces. It is not resilient to the loss of the right element. So what we are saying is that if the environment operated in exactly the worst way, which it probably didn't, but if the environment operated in exactly the worst way, indeed, the best thing the pilot could have done is what they did, which is jump out. And so we built this on further applications where we're trying to have now resilient trajectory tracking, so not just reachability for a multi-thrust spacecraft. Also something that I'm really interested in is kind of being a dictator. So opinion dynamics, trying to figure out if I'm in control of all of my broadcasting media, but I lose control of one of them, can I still get people to think what I want them to think? Clearly, I'm a person with many interests in these fields of manipulating people. So let me go to the third case now. So we went from actuator degradation, partial loss of control. Let's go to something most extreme now, actual change in dynamics. So I now have x dot equals f question mark of xu, where this f question mark is an unknown function. It's not a disturbance. It's not just finitely many unknown parameters. It is an unknown function. Interestingly, or not interestingly, but kind of classically robust and adaptive control. And I don't want it to seem like I'm bashing these two things. They're very useful and we use them. But they classically assume that the original target remains reachable. And what we care about is figuring out what makes it, saw this before, you should have, figuring out what is reachable. So motivation. You're wondering how that person survived. These were radio control things. I think that this was on purpose. So otherwise it would have been very difficult. So what we have now is a change in dynamics. And after one airplane crashed into another, it changed its physical properties substantially. The system can almost certainly not use the same control law to reach its target. It also may not be able to reach its original target using any control. So what we care about is what this is the system certifiably capable of doing, even if we don't yet know how. But can we somehow guarantee that, hey, I am able to reach this freeway? Then I'll think about how do I reach the freeway. So first of all, the answer generally is no, right? If I don't know anything about the system dynamics, if anything can happen in the next second, then obviously I'm not able to provide any guarantees whatsoever, right? I can't get anything out of nothing. But more generally, I can define something that I call, so I'm interested here in reachability, I can define something called the guaranteed reachable set. So if I'm at x0 right now, and I have the set of all the dynamics that are consistent with the current knowledge, so all possible truths, I can compute the reachable set for every possible truth. I can intersect these reachable sets, and certainly what is in the intersection is guaranteed to be reachable by every possible true dynamic. So I can at least write this down. Now, in theory, sure, yeah, just take the intersection, compute these reachable sets, and we're good. In practice, I am asking you to compute infinitely many reachable sets of a possibly nonlinear system and then intersect all of these reachable sets, right? This doesn't make any sense, and it especially doesn't make any sense if I ask you to do it online. So my idea here is I will create a meaningful under approximation of this thing that I can potentially, well, that I can do and I can hope to do it in real time. The way I'm going to do it is I'm going to find all the trajectories that are obtained by integrating guaranteed velocities. So what I mean to say is I will compute what I'm capable of doing at what I'm guaranteed to be capable of doing at a given time. And then I will compute the reachable set of that's going to be an ordinary differential inclusion. Using that, I will obtain at least some, if not all, guaranteed reachable states. Now, what are the velocities guaranteed at time t? Well, their velocities guaranteed at time 0. So what I can do right now, modulo some maximal system wildness. And again, we have this idea where if we know the system doesn't change a lot, then what I can do now, and I can probably do that in a minute from now. It doesn't really change. Now, instead of initially available velocities, I can compute with arbitrary small error, of course, if I have an arbitrary resolution of sensing and actuation and all of that, using some sort of an online learning or local system identification method, for instance, the learning part of my auto control. I can obtain a bound on the change of in the set of available velocities by using some Lipschitz property, and I can make a pretty strong play that I will know something about these bounds from physical laws, from design knowledge. I know that, hey, an elevon operates in a particular way. Even if something happened to the rest of the airplane, the elevon will still operate in some way that's in common with the previous. So we do have some side information. And so for control affine systems, it turns out that this set of guaranteed velocities at state X is an intersection of all the possible kind of infinitely many particularly parameterized, translated, dilated, rotated copies of the same object. So what I'm able to do now, modulo something squished, something with the Lipschitz function, whatever, with the Lipschitz bound, whatever it is. And so the idea is, okay, this is still a weird thing. It's an intersection of infinitely many objects. The initial idea is put a maximal ball in there. That will tell you at least some velocities that are guaranteed at every time, and then propagate this ball and then propagate the trajectories using it. We can do smarter things. We can fit a more complicated object, but still geometrically simple, polygon, ellipsoid, whatever it is. We can get a guaranteed reachable set then as a reachable set of a simple control system or an ordinary differential equation whose just at every time the available velocities are ball or ellipse or whatever it is. And in practice, that works at least over short time. So this is something that we've been playing with a model of a quadcopter. So if you look at the true reachable set is blue. Well, of course, we don't have the perfect knowledge of the dynamics. So it's not possible for us to figure out the true reachable set. This is not a computational issue. I just don't have the dynamics to figure it out. But I am able to figure out some sort of an under approximation. And I have two methods here. One is, I think, using the ball, and the other is using a polygon. As time progresses, these approximations get worse. But at least, again, over a short time, I'm able to. Okay, I'm done with all three of these things. Hopefully, I convinced you that there is meaningful work done in all three of these things. I still think there's a lot of meaningful work to be done in all three of these things. And so this is what I want to end my last few minutes on. So we only just started. We have a lot of technical assumptions that we make. We say that In the case of lots of control authority systems are linear. We're wrapping that up now. We're assuming some sort of full actuation, kind of a technical assumption that we have there. That's perhaps less interesting. More interestingly, we can be smarter. We should be able to use some structural knowledge of the undamaged part in unknown dynamics, not just say, hey, what I have now plus Lipschitz. There are parts of these dynamics that are possibly unchanged. I should be able to exploit them. Second, I need to be able to talk about not only what can be reached, but how to reach it. So after figuring out this guaranteed reachable set, I want to use some robust, myopic, adaptive methods that will allow me to actually reach what I'm planning to reach. Third of all, I shouldn't care just about reachability, right? If nothing else, I should care about some sort of safe reachability. Hey, reach a state while avoiding obstacles. At the very least, I should do that. Of course, there's computational limitations to what we do. There's time delays that we mentioned. That how can I see immediately what my opponent did? There's also partial observability. I can't see my entire state, especially if there's been damage and there's some damage in my sensing. We already started with the time delays. Delays hurt a lot. It turns out that as long as you have a non-zero delay in figuring out what your opponent can do, you can never perfectly cancel out the opponent. And so as we have this trajectory tracking, it kind of gets worse and worse over time. Provably gets worse and worse over time. So my medium-term goals here are basically developing these capabilities further. I'm interested in combining these scenarios. I'm interested in building a whole pipeline of end-to-end planning, learning, control. So I mostly talked about the first part, task assignment. What task can be provably completed? And then there's the second part. What do I need to know in order to gather the information that will allow me to complete this task? And then there's the third part, which is assured control. Okay, actually complete this task, collect the information and complete the task. I'm interested in more physics-based and design-based results, so exploitation of significant prior knowledge for better estimation. Long-term goals, I haven't even started talking about sensing. So we want to use sensors and perception to recognize the fault type, something that we kind of recognize right now. Hey, this actuator is not functioning. We want to do that using sensors and perception. We want to gather information, and ultimately this goes to fault detection work, the sensor fusion work, and state estimation. We want to do more complex missions, right? I don't just care about reaching a particular state. This is just a small maneuver. I might care about longer missions in high fidelity simulations. And ultimately that leads to automata and hybrid systems, because oftentimes different parts of the mission will be driven by different regimes of operations. And in the end, I care about onboard implementation. So whenever I implement something on board, I will have significant limits to real-time computation, and I will have time-delayed sensing, time-delayed control. All computations will take time. I'll need to care about that. I believe that the applications of this can go across domains, and that's why I'm really excited to talk to people throughout the GRASP lab and throughout UPenn. So we've been playing a little bit with a UAV. We're also playing with a simulator of a extraterrestrial lander, which is NASA ocean waters. We're playing with the RoboSimian, which is a physical hardware robot, and we're also interested in moving past the single vehicle, single autonomous system framework into something that is power grid, cyber security, so cyber networks, things like that. Summarize, if there's a few sentences that I want you to come out of this talk with. First, dealing with abrupt mid-mission events is crucial for emerging autonomy in challenging environments. We need to figure out how to deal with bad things happening. Classical robustness and adaptation are great things. I claim they are not enough. We need task assignment, and we need assured resilience. Our current results compute reachable states in all kinds of scenarios: unknown dynamics, actuator degradation, partial loss of control. Again, this is not enough. What we need is autonomous pipeline of task assignment, real-time learning, and control to accomplish challenging missions in complex environments. I acknowledge the NASA that gave me money for this, and the Air Force and the Discovery Partners Institute in Illinois. And most of all, I acknowledge my students. So the work on actuator degradation is led by my PhD student, Hamza Kabir, and with also some work by our previous undergrad, Melkior. The work on partial loss of control is led by my sadly soon to be graduating student Jean-Baptiste Bouvier and Kathleen Shu, who was an undergrad with us, who's now at MIT. And the work on unknown dynamics is led by my PhD student, Taha Shahba. Thank you. I would be so happy to talk to you about anything and everything, whether it's related to this or anything else in control, cheesesteaks or whatever it is. I'm really excited to talk. Thank you. Yes.
I guess I have one question. You said for the delayed case,
yeah,
what you're currently working on, that it's not possible to get guarantees.
Yeah.
On how, like,
not that it's not possible to get guarantees. It is not possible to assure that you can exactly reach and I guess stay at a desired state. And if you think about it, that's because think about that last mile just before you reach the desired state. You have this last time during which the opponent can always screw you up. So really what we're interested in developing is the guarantees, but there are different style of guarantees, not, hey, am I able to reach the exact state or not, but what is the ball that I can guarantee to be able to reach?
right, because if you have any point in the trajectory that is like, let's say early in the trajectory, and you have some interference from the adversary, it seems that would just, if you have delayed feedback, that would just decrease the size of the state space. But the closer you get, as opposed to the final goal, the smaller that set gets, and eventually back.
Yeah. So at the beginning, you don't really care that much. Then you start caring.
Yeah, because I mean, you get zero regret guarantees or like no regret guarantees for delayed feedback, but I suppose you don't have a point, right?
Yeah.
I guess that's a bit.
Yeah.
Okay.
Any other questions? We're coming up to what I want to do. Okay, so start comment on discrete time. You know, because you made some remark, and usually it's the sum of difficulties stays the same. But I'm just wondering what.
Yeah, so I can comment. I'm not sure that the comments will be particularly smart, but I would say this. On the level of ideas, all of these things that I'm playing with can still be done in discrete time. Now, on the kind of technical level, things will change. So, for instance, where we had that generalization of Grunwald lemma, we can't really have Grunwald lemma anymore. Now we need to have some sort of a discrete analog there. And so for a lot of these things where I kind of figure out, oh, the reachable set will not change by more than something, I would need to have new bounds. I ultimately believe that a lot of this work can be ported to discrete systems or discrete time systems. Technically, there might be challenges, but I think the ideas should.
Computationally, do you see that there could be an advantage?
So I would say this, and I would say that computationally, I think that there obviously will be an advantage simply from the fact that I can, in worst case, I can brute force things. And so things that, you know, if we don't know how to compute the reachable set of a nonlinear continuous system, at least I can do it for discrete. I'll just spend a lot of time. And so in that sense, sure, it's going to be easier. But I think that in kind of the practical sense, there will still be a difficulty in performing these computations that, you know, that will lead to blow up. And I think that there's still a benefit to kind of that geometric thing where I was saying, oh, hey, I won't just have a control system whose reachable set I'll try to, it'll be somehow geometrically easy reachable, so that I can kind of analytically figure out the reachable set without brute forcing it. And so I think that there would still need to be some of that.
When you had this work on like loss of control and actuator degradation, you had this Lipschitz bound on.
Yeah.
Right.
Yeah.
Can we do better if we have more stronger?
Yeah. So.
Kind of.
Yes, I would say that there's two possible ways to do that. One is the current way, or partially the current way, where okay, it's not Lipschitz, it's something slightly better than Lipschitz, but still over time it gets worse. Over time I get less and less knowledge, and so over time my kind of bounds disappear. I lose any guarantees. That can be done to an extent we do. I think there's a more interesting story there, which is structural knowledge, which is, hey, I know that the long-term behavior of the system will satisfy something, will have some similarity for with the long-term behavior of the original system. Can I use that? And so I can. For instance, there's the whole contractivity or stability notion that you can bring in, saying, hey, I knew that my old control law was stable, so if I know that the new control law is stable, can I do something? Yes, and we played with that, but it turns out that it's such a strong constraint that at that point you don't need to do any of this, right? You know that the system is already going to reach your state. So I think that there's kind of an interesting question that's kind of a meta question of what are the right assumptions to make that will make these problems challenging and interesting and yet not lead to blow up over an infinite horizon. And we're playing with some notions of kind of approximate contractivity, and hey, maybe it's converging to something, but that something isn't the original state. So what can I do? Yeah, these are good questions. Give me like 10 more students, couple more $1 million, 20 years, we're all over. Right. Yeah.
Maybe not a super well-formed question. For your resilience metrics, you're looking at whether like 0 is in the in the bounds. Is that 0 like for the full system state, or could you say it's for like some subset of dynamic stabilized?
Is what you're getting at? Let me just see. Is it the part where I said 0 is in the interior of something?
Yeah.
Yeah. So I guess the question that you're getting at here is, do I like? So first of all, this is not in the system state. This is in the it's related to the system state, but it's really kind of in velocity space. If we were working on manifolds, it would be some sort of a tangent. What I guess you're getting at is, and this is an interesting question, is what if I don't care about not being resilient to some part of these dynamics, right? What if I only care about, so not reachability in the state space, but reachability in the output space, where output is, I don't know, some coordinates or some function state. I think this is really interesting. We are not, or at least kind of with this, we have this kind of more applied paper on spacecraft, and they kind of care about specific outputs, but we have not developed the theory for this. I think this would be really interesting. And so because oftentimes, yeah, you might not be resilient to things, or you might not know a part of your dynamics, but you might not care about part of the dynamics anyways. Cares. Yeah. Yeah.
Yeah.
By the way, this is the most questions I've gotten recently, especially in cold. Yeah.
Motivated by failures of the medical class.
Sorry, can you
You're motivated by the failure of the fast control. That's situation. So avoiding the connection of these decisions to the bus control. Some connection can maybe, I don't know, maybe, I mean, some
Well, I think that, okay, first, I think that to the same extent that I think that's a very good question. To the same extent that, me using the word resilience or resilient control is kind of an all-encompassing buzzword. Robust control is for many people many different things. In my kind of, the way I think of robust control is we care about small disturbances, and we care about a more monolithic rather than adaptive way of dealing with these disturbances. So care about me saying at the beginning, I know these are the things that might happen, and I will figure out the control law that deals with the worst case of these things. And the same motivation still holds here. It's just that it's no longer kind of a bounded disturbance story. It is now a story of disturbances that are somehow, well, they're not really disturbances anymore, and also their structure is different. We no longer care about the size of the disturbance. Instead, we say, oh, the disturbance can lie anywhere in this set, or something like that. And so there is a relationship here, and I don't want to seem like I'm bashing at all robust control. I think that ultimately the questions we're interested in.
But wouldn't you say that most robust controller is just unconstrained?
Right. I mean that's, yeah. Yeah. So I think that, yeah, I think that the motivation is kind of similar, but on the other hand, I think that there's a lot of things that robust control can't really do, can't really consider. So what I'm saying is, yeah, I could have called my, the thing that I'm selling here, oh, extension of robust control. To some extent, everything is robust, but yeah, I agree. You want?
So if I guess you didn't touch upon it, there is perception uncertainty. And if a part of the state is unobserved, or you cannot.
Yeah, I did touch on it in the slide where I said these are the things I don't know how to do. No, I'm partially joking, but yeah, whatever question you're about to ask me, yeah, I fully agree that these are important questions that oftentimes when you lose, when your dynamics change, also your perception model changes in some way. You will get different poor, incomplete observations. You'll have to deal with all of that. I think that's really interesting theoretically and in practice. I want to say that, oh, this big idea of, hey, I will still want to figure out kind of the guaranteed velocities or guaranteed reachability. Yeah, this still holds, but how to actually implement